Okay, so we're moving into our Ponchon-Savarit now. In this case, we're switching from our benzene toluene mixture that we had initially in our binary XY diagram. But yeah, again, we're going to be using these conditions listed here for graphing our Ponchon-Savarit. And then after we generate those diagrams using a loop, we'll talk about changing the reflux ratios and the effect they have on our diagram. So actually we'll also be generating not just our Ponchon-Savarit, but in the column next to it, the binary XY diagram, essentially our McCabe-Thiele, our staircase with our operating lines. So I have made a couple notes here just of the changes we have that's not explicit or obvious in our problem statement. So again, changing from benzene to toluene. The idea of this is with the mixture we used last time, whatever azeotrope it was. I think it was methanol water or something. Um, that was, I think, in the second part of this series of problem statements. Um, the whole idea of the azeotrope was to see what it looked like on the binary XY. But now that we're with the Ponchon-Savarit, it's better to have a mixture that's harder to separate, since with azeotropes, obviously, I think I mentioned this in the last video, they're harder to separate past the azeotrope, that point where the vapor in compositions or vapor and liquid mole fractions are identical. And then obviously before that point, before their azeotropes, if you remember the curve, there was a much bigger curve deviating from the 45-degree line. So obviously there's easier separation before the azeotrope. So we'll do, I think this problem asks methanol-isopropanol. Essentially, you're going to get the same kind of graphs if you do either of these two. There'll be more stages, and that's exactly what we want in our plot. So it's more visual. You can see the lines and what's happening. So I think I already explained the Ponchon-Savarit in the last video. I think we can just go straight to our our collab, sorry. So we'll go with that. And this was our last code we had. I believe, yeah, I could have talked about this, man. So our azeotrope and then the bigger curve, so better separation here. And then this was our bubble temperature XY diagram. So I'm going to go ahead and change it. What was it on my iPad? Methanol and then isopropyl. Oh, actually, let me make a copy of this since this is NRTL. It has everything from isopropanol water. It just keeps everything, and we'll have this separate. So how about that? Then I have some stuff pulled up here. Underwood. Oh yeah, I had that listed. So we had Underwood and the Fenske equation. I'll talk about those once we're finished graphing. But no, that's coming up. And then this is mostly for me for my colors. So I'll delete that. And then we have dash dotted lines. I think I'll use this for the tie lines, which I mentioned the Ponchon-Savarit. I'll say it now. It was the endpoints of a tie line are these stages that are, or compositions that are the liquid and vapor mole fractions that are in equilibrium with each other. So I'll bring it up again when we're actually graphing, but that's what that's for. I'll make those dashed lines. Those are copies, so I'll go ahead and just delete this, and then go. And then it is methanol isopropanol, right? Yeah, isopropanol. Okay. And then I think we could just hit run all. I have my given conditions here posted already. And I'll go ahead and just change this to Ponchon-Savarit. I think it's 1T. Yeah. Okay, so while this is running, I guess I'll talk about the sort of general plan. First, we're gonna get our enthalpies. So with our enthalpies, well, I guess general plan outlining everything. So enthalpies, then after we grab our enthalpies of our two mixtures, well, actually, this is for our more volatile component. So it's going to be of the vapor and the liquid of our more volatile component, those two enthalpies. And then after we grab those, we'll be graphing lines in between. Wow, this is slow. Graphing lines in between our difference points, if you remember on the Ponchon-Savarit. So we'll need to calculate those, calculate the condenser cooling, and then for the stripping section, the boiler power. I think it finished. And then after we connect all those lines, we'll go ahead and loop them Well, at least we'll start with the rectifying and then use the next vapor mole fraction to calculate the next liquid mole fraction using equilibrium. And then with the liquid mole fraction, we connect that to our difference point, and then the intersection of that with the vapor enthalpy is our vapor composition. So again, I'll go into more detail here. Oh yeah, I don't know why this is failing actually, but we actually don't need these for our azeotrope. I'll go ahead and just delete these. Not our focus. But we can focus on our constants here. So actually, I don't think I need my iPad for a while, so I'll put it on the side. Yeah. What are we doing? So we have our given constants. You'll notice that we limited ourselves with a recovery rate or recovery percentage. And this is so that we don't overexceed our feed that we're putting in. Again, the most simple mistake that's common when defining our distillation column is defining a distillate flow or a distillate composition that exceeds our feed. So that's why we have this recovery percentage. And doing so basically limits all the other flows. So again, same deal when we graphed our McCabe-Thiele. Also applies here where we're defining our column. And using that, we can use our mass balances to basically have expressions for everything else. So if I write our expression for the distillate, it's something like our distillate flow times our distillate mole fraction times our distillate flow is equal to our feed times our feed fraction. That is obviously the more volatile component. However, we have a, guess I can put it here. We now have a recovery rate of that feed that we want to recover in our distillate. So that's why I put the percentage that we want to recover on this side, since that's the percentage of the feed that we are recovering in our distillate. So now, obviously, we already have our distillate, I don't know, composition we want to achieve. So with that being defined, to get our distillate flow rate, we simply just divide over our distillate mole fraction. So that's our distillate defined. I'll have them down here as we define them. So with our distillate, what else can we define? So we have our condenser defined pretty much. Now we just need our vapor, or not our vapor, our boiler defined. So with our boiler, we have the same exact mole balance, just a little slightly different. So we have mole fraction of the bottoms times our bottoms flow rate, and pretty much it's the exact same thing. However, instead of recovery of the distillate, we have a recovery of the bottoms. So there's a couple of things here that are missing and that aren't defined. But since we already know some other things, we do a total mole balance of, I guess, mass balance of our feed and our distillate and our bottoms. If you remember, feed equals, well, in equals out. So feed equals bottoms plus distillate. And you'll notice that we have our distillate and our feed already. So if I just manipulate that, it becomes, let me zoom in on this. That might be too much. Maybe something like that. So if we manipulate this expression, our mass balance, its bottoms is equal to F minus D. We subtracted our distillate from our feed, and whatever is left over is our bottoms. So that's our bottoms. What else are we missing? So we have bottoms. So this recovery, obviously, if we're taking out 99% of our feed, the other 1% has to go to our bottoms. So that's our recovery of the bottoms is simply, well, I could do something like, obviously this has to add up to 1 since it's coming out of the feed. So maybe like distillate mole fraction plus our recovery, I should say. Recovery, recovery of our distillate plus recovery of our bottoms equals 1. And you'll actually notice if I defined it the other way around, if I did a composition of the distillate plus the composition of the bottoms equals 1. These are, they kind of yield the same expressions if I were to do it in terms of our mole fractions. But for now, let's just do it this way. I've tried it the other way and you still get the same graph, so that's all that matters. But yeah, we'll define our composition this way so that our recovery this way so that our composition isn't just a value we define. So it's a value that's limited through these expressions of the recovery. So let's define our recovery of the bottom. So if I want recovery of the bottoms, I would subtract 1 minus our recovery of our distillate. RD. Okay. can delete that. And now we have everything defined here. We just need to get our bottoms composition by dividing the bottoms across. So that's our Python algebra. And let's go ahead and see what these look like. So distillate, bottoms, recovery in the bottoms, and well, we don't need that, but bottoms mole fraction. Oh, I didn't shift enter up here. So not bad. Distillate flow rate up top is lower than our bottoms flow rate. Kind of makes sense. We have a higher recovery in our distillate. And then this is our bottoms mole fraction composition. So 0.01, pretty close, 0.99, 0.01. So now we have this variability of our, not variability, but it's determined based as a limited by how we defined our recovery up here. So that's why you see all these numbers carrying over, and it's not just set numbers that we define. Okay. So those are good. I guess next we want to, so I said we'll graph our enthalpies. Our enthalpies are going to be coming from our equilibrium that we graphed here. So notice this is not an azeotrope now. It's a normal, well, quote unquote normal line that we've seen before. So this is the bubble temperature XY, and then this was the binary XY. So since we have these temperatures and liquid mole fraction, or yeah, liquid mole fraction and vapor mole fractions, we'll want to use those for our enthalpies, and we actually have a handy tool for that already. I think it's already imported. Yep, props. So I believe we'll be using the enthalpy of the liquid, so P.HL and P.HV for heat of vaporization. And notice that if you see, oh, sorry, my keyboard is falling. Notice that they're a function that take a number of moles of the liquid and a temperature. So we actually already have those. We'll be taking this on a 1 molar basis, where we use the X1s and the Y1s as supplying, as a respectively for the heat of the liquid, we have our number of moles of the liquid. So I guess we can just take an example here with our, I think we have this defined already. X and a temperature. So notice that this is applied as a composition. This is composition of methanol and isopropanol. And then how we graphed it down here was with the more volatile component. So X1, we need to supply that right here as another composition. So I'll go ahead and use that X and T, the composition, the array of compositions, and our temperature. Then we get a number. So this number is the heat of the liquid associated with 1 mole of the methanol and isopropanol, right? I changed that. Okay. And it's 1 mole because we add up to 1. And remember, it needs to obviously be more than 1. That's how we defined our properties. So we need 2 inputs, and remember that this X is an array of, or a list of 2. And then this temperature is what we had earlier, 373. So eventually what we want to do is, once we have these enthalpies graphed, or I guess stored in a list is what we're doing, we're going to be doing kind of similar thing here where we iterate based on all the X1s, our temperatures, our mole fractions, and iterating our liquid enthalpies and our vapor enthalpies, storing those as a list since they're based on an equilibrium. And then based on that equilibrium of enthalpies, essentially, we do an Akima interpolation so that we can get any point we want and then graph that basically on another plot here, so that we have an entire range of enthalpies and yeah, for our graph. Since again, as I discussed in the previous video, we had for Ponchon-Savarit, the y-axis was in terms of enthalpies, and the lines on top and the bottom were the vapor and liquid enthalpies respectively, with obviously the vapor being higher. Okay. Yeah, I can keep this since we'll reference it. I can supply an X1. So remember, this is 0.4 for our more volatile component, methanol. If I supply 0.4 here and the same temperature, well, it'll be the same temperature. We should get the exact same, oh, this is bubble pressure, sorry. We should get the exact same liquid enthalpy once we do our interpolation. So all that being said, we'll go ahead and do that. So I said we were going to do lists, but you know what? Let's just look at our x1, y1s and t's. So I'll do something like I'll do like a practice loop or a practice list. I don't know how you want to say this, but if I go for I and maybe I won't loop it yet. Maybe I'll just look at it. So if we zip those together, remember zip, I don't remember when we used this. I think it was when we did our staircase. We zipped together pairs of points. So in this case, we're also doing points of liquid mole fraction, vapor mole fraction, but also our temperatures. We want the first point or first data point in all those arrays to essentially match up. So I'll do something like, can I do VStack? Well, let me do that. And then if I zip together, or is it zip and then I stack? Let's try it the other way around. I actually haven't done this. We'll see. See if it's wrong or not. So I have x1s, y1s, and t's that I want to look at. Oh, this needs to be a list of some kind. Well, of course, it won't let me look at it. Maybe print it as a list. Okay, great. Maybe if I do this. Sorry, this is me playing around. I just want to look at it. Nope. Okay. Yeah, let's do it how I tried it before. So I zip together and I v-stack them. Vertical stack is what that means. So I stack them along the columns. What am I doing? X1s, X1s, Y1s, and T's. All right, if this takes too long, I'm just going to pause it and then show it, because I don't want to waste too much time on this. There we go. Okay, so we have each of our arrays. So we start with our x1s. This was the MP lin space, so I believe it's 51 or 101. Okay, from 0 to 1, so that we include 1. That's why it's 101, not 100. Second array is our y1s, so right here, corresponding obviously to our liquid mole fractions, and then our temperatures. So 355 all the way to 330. So it looks like we're decreasing temperature for a higher liquid mole fraction. Yeah, essentially I want to grab each of the first points of these arrays together and unpack them. That's what this zip is doing. VStack is here for me to just see them in a uniform fashion. Well, this obviously isn't the best, but this is how I kind of tinkered with it. I was practicing. So essentially we want to zip these together, and then in our loop we'll unpack them as, well, what they are, the x, y's, and t's. So the mole fractions and the temperature. So I'll just delete this. I think I can keep this, but then I'll delete the zip. So something like this. So, and get rid of the VStack. Okay, I'll do our loop. I'll do for I. Well, will it let me do for I? Let's see. It might need to be in one thing. Oh no. Okay. So looks like they do come as oh, this is perfect. So they're already in points that correspond to each other. So remember, this y1 is in equilibrium from using our bubble temperature. Of course, non-ideal with our NRTL model. And then these are unpacked, or these are zipped together, I should say, all their points together. So yeah, this is exactly what I want. But now instead of using I as for each row of points, or at least for each iteration of the points in each array, I want to unpack those and use those for our heat of liquid and heat of vaporization. So I'll go ahead and unpack that. So we have do x1, y1, and t, since these are plural. And then instead of printing, what do we want to do? So I unpack them, and oh, we need an a list. Not a list. We need a list. So forgot to put that. We have our heat of liquids, the list. We're storing these as essentially the equilibrium points of our vapors, our enthalpies that we'll interpolate from. So those are our lists. And then what we want to do is append something to those lists. So we're appending the heat of the liquid to the list. Maybe I can just call these equilibrium since I don't like having them as the same name, but eventually this will be rewritten. So I'll do like equilibrium maybe. So I don't know. So obviously we're adding something to the list. It's a value, and that value is our props from our p.hl. So this is actually the expression that gets that value right here. And then now remember we supply a composition. So this is a composition of our liquids. So this is our x1. So we need a composition of our liquids. This is just the more volatile component. So what I can do here, if I have our more volatile component, well, it's a binary mixture. The other mole fraction or liquid mole fraction has to be the other half. So we subtract from 1 in that case. And then this needs to be an array. Remember our x here. This essentially these two expressions are the same. I'm just supplying x as a array using our iteration of x1s. Again, x1 is the liquid mole fraction. So I don't know why it says that. So 1 minus x1 is what it should be. But this needs to be an array, I believe, since x up here, yeah, we need to define it as a array or a list of our composition. So I put brackets around that to denote that. And then the last remaining parameter is our temperature here. So we have our moles of our liquid supplied, and then we have our temperature. So our temperatures are being unpacked right there. So that matches up perfectly. And then heat of vaporization, it's pretty much the exact same thing, except we now use our y1s as the mole fraction. So again, with liquid, there's also a p.hv, the properties we use from our CHG tools GitHub import. It gets the vaporization of the composition based on the moles of vapor this time. So again, corresponding whatever we need to. So y1, 1 minus y1. And the list, and then the same temperature that corresponds to that y1. And then I think let's just take a look at one of them. Let's look at HO, our list. Yeah. So it actually got filled, nice. So I wonder if I can correspond these already. If I supply, well, I need to supply a that's right, we're gonna interpolate these first. So let's interpolate. If you remember, did we do a spline here? Yeah, right here. So interpolation, spline, first the same thing. We're using our Akima one-dimensional interpolator given a set of data points. So we're gonna be inputting some variable, or yeah, inputting some variable, give me this next variable. So in our case, it'll be both the heat of liquids and the heat of vaporizations. So I'll do something like HL is equal to Akima spline. So given, so liquids take obviously liquid mole fractions. So given an x1, so this is based off our x1s, give me a heat of liquid that's in equilibrium with that. Oh, I mean, technically it's not equilibrium, it's the heat of liquid at that, but that's what I named that list. I don't know. The reason why I put this equilibrium is so we don't get confused, but essentially the code is rewriting this so that it won't mix up these two if they're both called equal HL for enthalpy of the liquid. So it looks a little weird, but that's the reasoning behind it. I just don't want to confuse the two names. Zoom in a little bit. I mean, we can try it before we do the other one. So maybe something like so this was X referred to 0.4, right, of our methanol. So that's what we're doing. Methanol is more volatile, so I'll do 0.4, and then at the same temperature. And hopefully this should work. Oh, that's not good. Maybe T is not looking at the right T. It's looking at the T here. So maybe, was it 373? Let's try that. Oh, is it a problem with me running everything, perhaps? Since we do want these to match up. Yeah, I was having trouble with this earlier where if I took the spline out, it'd be reading something from itself, I would think, and it would crash. So that's why I'm putting the spline with the data. Okay, so that's interesting. It's not actually taking the spline from. Oh, okay. Well, that's not good. Let me try something. So I'll do, instead of comparing it to here, I will move it down and do what I did in my practice, where I compared it to looking at the heat of liquids, and then our first point was at 0. I think so, right? 0. Okay, so yeah, let's try that. Oh, it won't let me look at it? What now? Oh, I removed the interpolator. What am I doing? I need to look at the list. Sorry. There we go. Okay, so the first point should correspond to when x is 0. And let's see if this is true. The temperature, I actually don't know what the temperature was. Will it work if I put T? So interesting. Is there nothing happening with this? Given liquid. Yeah, I don't know what the starting temperature is, honestly. Let me look at the T's. Honestly, this is the last thing I thought I'd be having problems with. So let me copy paste this and put it here. And if this doesn't work, okay, keep getting 0. So, okay, I'll go ahead and try to figure out what's happening here. You know what? I found it. I'm inputting too many things. It's just one thing I'm inputting. Okay, let's try this again. So if I put 0.4, let's it should match up with this. So shift enter. Okay, it does not match up, but it's pretty close. I assume this would have to do with the interpolation. If I look at the actual, maybe if I would do 0 and match it up with our actual list. So our list, it starts at 0, remember? X1 starts at 0. So this enthalpy is the first iteration, so it matches up with the first X1 we input, which is 0. So this enthalpy 307,000 negative should correspond with this. So interpolates exactly. And I'm assuming the error comes from the lack of interpolations that we have, or a lack of data. If we had more data, it'd probably interpolate better. So yeah, 279116, pretty close. I imagine if I increase this to, I don't know, something stupid like 501. Let's see how long this takes. I should not show that. They're gonna yell at me. It might run it. We'll see. So 500 is a lot of points, so we'll see if the interpolation does get better, proving what I think. But it may take some time. And let's run this. No, I guess that's the interpolation, since we don't go to 0.4, I'm assuming, maybe. But yeah. Anyways, we'll do the exact same thing for our heat of vaporization. So go ahead and do that. We can match it up too and try to see if it matches up. So I'll just copy paste this. And then now we want to input a y. For some y, give me the heat of vaporization, and it's basing it off of this list of values that we stored. So let me just put it back at 101 and do that. And let's try to match it up to see if it works. So we have our x at t, and then we're comparing this to our spline at 0.4. 24, yeah, 1,000 joules, not bad. Again, that's just the limiter of our spline. If we wanted to do this normally, I believe we'd have to supply a temperature with our dew points and our that gets into going past our bubble temperature and RTL. We'd have to do the dew side of that, which is a bit more complicated. So that's why we're interpolating here for the enthalpies. Yeah, since the temperature you would need would correspond to the first liquid. So yeah, that's why we're interpolating. I think we can just graph this, honestly. So let me just copy paste this. We can keep that. And this is our initialization. I don't know what that is. Okay. So let me change all of this to Fig 2. Again, multi-cursor, Control Shift L, so Fig2. And then I might just comment these out. Eventually we will do 2 plots like we did before. The right-hand side again, column 2 will be the McCabe Thiel. Am I recording? Okay. So I'll keep those for now, but essentially here we're wanting to graph the heat of vaporization, heat of liquids. So we actually already have a list of x1s and y1s, and the slope shouldn't change too much. Well, the line shouldn't change too much is what I should say, since I think in class the way we did this was we defined a z. So z could be liquid and mole, or yeah, liquid or mole fractions. That's why we define it as z, and then we graph our enthalpies, and then use those enthalpies splined or interpolating from the z. So we can graph any number of points, but again, if we just connect the lines, it should be the exact same. So again, liquid mole fractions correspond to our x1s, or I guess our enthalpies, I should say, correspond with the x1s, and then the vapor enthalpies correspond with our vapor mole fractions. And then I think I can just graph this, no? Let's try it. Awesome. Okay. We got lines. And yes, remember what I said earlier about the slope being upright in Ponchon-Savarit, the previous video. Essentially all that means is the heat of formation for, I think, what's our other component? Isopropanol? Yeah, isopropanol is much bigger. It's going to release more energy. So that's why for a whole component of methanol, our more volatile component, it's a much lower energy release, since obviously with isopropanol, that would be when methanol is 0. You have more energy released, and obviously a greater heat of vaporization and a greater enthalpy of the liquid. And then conversely with methanol, you need less heat of vaporization to vaporize liquid, since it's more volatile. Remember, the negatives are in terms of magnitude and energy released. Okay, that's that. I think that's all I want to do. I don't think I change any colors from here. What do we do next? So we have our enthalpies. I think the next thing is we just graph our points. So graphing our points, let's just start here, honestly. I'll put that up. Start from down here. So I guess we initialize. So starting from the condenser, we work our way down. So initialize at the condenser that liquid mole fraction. So maybe condenser works. Condenser mole frac. Okay. So we're gonna define our vapor mole fraction. Remember our condenser. I can just go back to this real quick. So right here, we defined our starting point right here. Again, in equilibrium, we have, at least for this 0 stage, the condenser, this distillate, this Y1, are in equilibrium with each other. So the next point we're trying to get is this X1. Again, since this X0 is the same thing as this XD, and that's mainly because of equilibrium. They're coming in and out of the same stage. So that's how we started our Ponchon-Savarit. These essentially just this point, and then we're trying to get our equilibrium here at our x1. So that's what we'll be doing. And while I'm here, after that, so this is the equilibrium. We connect that to. Again, our points are already. I think we have an Akima spline, or we might not have it. We might have to code that. But we have one for the y, but we need one for the x to interpolate the equilibrium between. If I say give me a y, given a y, give me the liquid mole fraction in equilibrium. So that's this green line we have right here. And after we get this composition, remember we draw our intersection to the difference point up here. And then our intersection point is the vapor mole fraction. And obviously this is a greater separation from our liquid mole fraction, again, since the vapor is more enriched in our volatile component. And also this means that when we get our intersection, so that'll be with a root scalar, will be, remember that the intersection comes from setting our two equations, if I can find them. So that's right here, setting these equations equal to each other to solve for essentially the next y. So the y from this stage coming up. So again, it's something like if we have our y1, we get our x1. Oh my goodness, get our x1. And with the x1, we do our material and energy balance to get the passing stream. So again, remember this whole idea of Ponchon-Savarit comes from non-constant molar overflows. So that's why we're doing an energy balance associated with this, since the heat of vaporization does not change or is changing with composition. And then the whole process repeats. Remember, this was all with, we can draw this line because of similar triangle. So you'll actually be able to see that when we actually do the intersections, and it won't be not lining up with the points as it does with my rough drawing here. Okay, hopefully that's squared away. That kind of makes sense. We'll move back to our collab. Yeah, so we want to initialize, I'll just call this y. So y as the distillate, remember they're at equilibrium. And then now, remember, we're trying to get the liquid mole fraction, so the equilibrium from the same stage. Again, this will be the tie line, so we'll need to grab the, I think we said we're going to interpolate that, so we'll do x equals, I don't know, x1 spline of that. And I don't think, do we have one? No, we don't. Okay, so, oh, right here. Okay, so we do have a y, but we need an x. So it's the exact same idea. Given a, so this will be an x1 spline. Given the set of y's, give me the x corresponding to it based on our data that we used earlier. Again, the binary xy diagram, that's the exact same data that we're interpolating from. So if I do x1 spline, and actually I already have an example here. So given a liquid mole fraction of 0.4, it gave me a y1 of 0.568. So if I give it the same mole fraction, vapor mole fraction, I should get the same liquid mole fraction I put in. Let's see. There you go, it works. Okay. So if that works, then we know this is interpolating correctly. I'll keep it together for now. So this is getting get equilibrium of next liquid mole fraction. So again, if this is y, well, it is y1, this has to be x2. So it's coming from this, I guess, the x1. I'm sorry, yes. If it's from the same stage, then the subscripts match up. So I'm sorry, it should be, if you know y1, then you know x1 coming from the stage below. So with that, did we just graph this? Yeah, we need to connect our x. So remember, this is a point corresponding on our liquid enthalpy line. So that'll be, we'll interpolate that using the x value. So we'll do like HL, the enthalpy given a the more volatile component of the liquid mole fraction, give me the enthalpy. So that's what it's interpolating on, remember, from our equilibrium that we made a list out of, and now that we're interpolating from. So I mean, we can try. I think we're still missing something, but it's not clicking for me yet. So this will actually be points, pairs of points. Ah, yes, we need the other pair of points. So I guess we can start. We know one pair. So our first pair is obviously for our next x, and this corresponds to what did I say? A liquid enthalpy, right? So liquid enthalpy given that x, and then now our second point, we're connecting to the difference line. So yeah, that difference point needs to be defined so that we can actually do that right here. So maybe something like our difference point. So maybe like, I think we called it delta R in our example. And actually before that, in the delta R, remember we have our QC, our condensing power, that needs to be defined as well. Yeah, so I mean, yeah, I might be able to just put this, since I think I actually wrote this out already. So if we go here, let me just split this. Can I do that? This one. Okay. Yeah, we actually wrote it here already. So delta R is already defined too. Awesome. So hopefully you can, it's probably the closest I can get. So we need to find, oh, well, QC, we actually do need, I will need to write on the not whiteboard, my iPad, but we can define our delta R, but know that we'll also need to define our QC. So I'll have a QC ready for us when we derive that. Well, not really derive, it's from an energy balance. But we have delta R is equal to, and it is QC over D. Remember, distillate is already defined. And then HD, remember, HD is defining the enthalpy associated with the distillate, but the distillate is a liquid, so we use the enthalpy of the liquid associated with the composition of the distillate. So that's just XD. Now QC is the one we need to worry about. Well, not really worry about, but kind of see where it's coming from. Yeah, let's talk about this. Over. Take a drink here. So looking at our condenser, how do we know how much condensing power we need? So this is a total condenser, meaning that all the vapor coming up must be equal to the moles coming out. So we need to get that enthalpy of, I guess, condensation, maybe. So that is, well, since we know these compositions and we have an interpolator for our enthalpies, we know these compositions, we have an interpolator, so we should be able to get the enthalpies of what's going in and what's coming out. Essentially, these are the same composition, so those will be the same enthalpy. What else? And then we're fully condensing our vapor. So let me write this out, actually. So we have our condensation power, how much power we need to condense all of that. So based on our vapor coming up, so there's a vapor flow rate associated with that. So our vapor, and then we multiply this by how much it takes to actually condense. So this is condensing power, I guess condensing enthalpy. And then let's do this one at a time here. So remember, condensing enthalpy, we have our enthalpy of the vapor coming in and the enthalpy of the liquid coming out. And obviously the two liquids coming out are the same composition, so we don't need to do it more than once. We just look at these two, and they're the same composition at XD, the distillate. So I guess I should note that this is the distillate. And actually, this is also the distillate as well, because they are in equilibrium. They have the same composition. So what is the change in enthalpy between these two compositions at two phases? Well, we know vapor is higher, so we just subtract the two. It's a difference. Okay, so vapor flow rates. How do we get vapor flow rate? Well, we can do our balance where, did we do that already? We've done this a million times. Right here, vapor is equal to the liquid coming out below and the distillate coming, well, we take that out. So this is balanced at our condenser. So if we talk about that, maybe right here, vapor equals liquid coming down from the condenser at stage 0 is the condenser, and then plus a distillate. And then we have our reflux is defined as our liquid we return, our reflux, the liquid that's coming down, and divided by our distillate. And we're trying to define V, since we don't have that defined already, but we do have our reflux and our distillate. So we need to define V in terms of our reflux and distillate. Remember, these are parameters we already defined in our initial conditions. So, I don't know, we can just plug things in, honestly. So liquid should be substituted for R and D. So that's just reflux times distillate. So if we plug that in, vapor is now, I'm sure you can see it. Okay. Reflux plus distillate. Oh, wow. Okay. So we actually are, in terms of everything we know. Now we can, well, we can just factor that. So D R plus 1. And that just gets shoved right there. So I can just rewrite that, honestly. D R plus 1. Multiply. Okay. I think that's it. Yeah, let's try it. Okay. Ponchon-Savarit. Okay. So actually let's just use the one note. Where are we? On here. Yeah, okay. So where are we here? Right here, QC. So we're defining QC as D times R plus 1, so distillate times the reflux ratio plus 1. That was with our substitution with the liquid at the condenser, that condenser mass balance, and then we're multiplying that since that's our vapor flow rate. And then we have the difference in enthalpies. So I think we just use our interpolation, right, of our vapor. So that's at our distillate composition, and then we subtract our liquid enthalpy at the same composition, and multiplying by the flow rate since that's how much is getting condensed. Let's take a look at both of these actually. Yeah, pretty comparable. Notice that it doesn't change that much. Well, actually, are we subtracting this? Did I make a mistake? Oh no, it is negative. I'm sorry. Heat of liquid is negative. It's yeah, it's very negative, 200,000. So if we're adding those together, um, yeah, liquid down here. Sorry, yeah, 200,000. I said, but yeah, 200, and then we are dividing by distillate. So, uh, essentially the difference point is a very big number, but it is higher above here. The power of the difference point is associating the amount of power we are taking out, well, with a condenser in this case, with the distillate we're taking out, it's a ratio between the two, so that's joules per mole. And then obviously this is also another enthalpy, joules per mole. Okay. Yeah, is that it? Let's see. What happened? Now moving on. That's right, we were connecting our points, so it needs to connect from... Actually, am I getting ahead of myself? This is for the I haven't even graphed um the tie line, so let's do that first. So this is actually going to be the difference point. Actually, I can copy this, can't I? So I'll call it the MEV point for it's a mass energy balance that we're doing the intersection of. So this will be, well, B is balance, so MEV line, and this will be the tie line. So we're still doing the same point, this liquid mole fraction, and then interpolating that on the enthalpy line for the liquid, and then we connect that to our the vapor coming up. So that was HVY, and let's see if this works. Nice. Okay. So yeah, that's perfect, honestly. I don't think I need to be split screen anymore. Sorry. So I actually want to do some cosmetic stuff here, so I'm gonna add let's see, what is it called? Line dash, I think. Dash equals dot, so we have a line, it's line dash. I like the dash. Just showcase how it's different since we're gonna have multiple lines on this. So dot, and then let me pick my RGB color I want. I think we want to do green, right? So maybe this green, 51, 153. Sorry. RGB 151. Oh no, what happened? Okay, we're good. 51, 153. And 102. I like the green. Oh, yeah, comma. There we go. We got green. Okay. Now this is where we do our connecting to our difference point, and our difference point is associated with our distillate, and then we graph our delta R is our difference point, so delta R. I think that's it. Weird, since we already have it. Okay, cool. Yeah, that is very high up. Okay. Yeah, and let me change this color again too. So I'll go line color. I like this blue. I might have made it white the other time, but anyway. 204, 204. 255. Comma. Yep. Not bad. Okay. Yeah. What else are we missing? So now we need to get the intersection so we can start looping this. So that will be okay. Wow, we're already at an hour. Okay. Um, let's speed things up a little. What are we doing? So we need the intersection. All right, that was a root. So with a root, we have root scalar, but we do need a function. So our function we can put up here. I don't want to define the function. Well, we're not in a loop yet, so there's no harm in putting it now. So actually I'll do that. But remember that if we put a function, if we keep redefining our function within a loop, that'll slow down our loop. Oh, I'm muted. Okay, so there we go. So what are we doing? We need to do a function. So we'll call this a rectifying equation. An intersection. MEB balance. Solve y2. I don't know. I'll just call it rectifying. Okay. We input our y. Well, this will be the next y. So I'll call it y2, like we did in class. And then we supply an x as well, since we need to solve the equation with more than with all the variables needed. But notice that in our function, it's only solving for one variable, so we'll have to provide x as a argument. The parameters for our root scalar. Again, root scalar only solves for one value. So we will want to return our equation. So actually we need to split for this one. Where are we? Leave right here. Oh my god. What's happening? There we go. So we're setting these equal to each other. I mean, they are already set equal to each other, but we want to zero out these equations so that we can solve for yn plus 1, essentially y2. So the stage below. So y2, we already have this. Remember, qc over d plus hd. That is our delta r. So I go delta r and minus our heat of vaporization interpolated from our y2 from the stage below. And then I divide that by the same thing, heat of vaporization at the stage below. Type, can you see that? Okay. And I subtract heat of the liquid interpolated from the current x mole fraction. Is that it? Oh, I'm missing a parenthesis. And then we subtract this equation relating this is our mass balance, our mole fractions. So we subtract that, do the exact same thing. So this is x at our distillate minus our, what is this? Our y2. So yeah, vapor mole fraction from the stage below again, and then y2 again, and minus x. And then remember, xn refers to the liquid mole fraction at the current stage. So what's happening here? Okay. I think we're good. Yeah, let's go back full screen. And then it's a little scary doing this all at once, so I'll move this to see on the outside we're actually doing it correctly. And then so we want to zero out this equation, our function. I think root scalar is just brackets, right? So bracket And then remember how we said earlier, it's lying between the distillate and our current x. So supply that as a tuple, and the tuple or list, I can't remember. I think bracket is a bracket, so it's between our current x and our distillate, but we don't want to be on the exact points, so we add very small number and then subtract the very small number. So that's, we are still, I mean, I could make this even bigger. How far does it go to? Like, how many digits precision Python? 17? Okay. What's that 64 there too? I don't know, 17? Why not? Yeah, let's see if this works. Uh-oh. Oh, yes, good. Arguments. I even said it, I forgot. Okay, so arguments, we supply that since we didn't, we're solving for one variable, we're not solving for two, so we need to supply the arguments of x, and then we have a comma in case there are more parameters. I think that's it. Let's go, converged. Okay, so now this is our new y2. So notice this is 979. If we look down here, oops, take a look at this, see if it actually lies between 979. Yeah, it's actually in between here. So somewhere here, like right there, maybe. Okay, let's graph that. So this will be our y2. Let's see if I do this right. We want the root attribute, dot root, and let's look at it. Awesome. I don't know why it's saying that. Very funny since it worked earlier. Okay. Yeah, I think we just put this all back in. Put this back right here. And notice that this y2 will eventually be the next y we use to take the equilibrium of. So we'll have another intersection. We'll have another point here. Well, I guess it's just right here, right? 97. Yeah, it's actually right there. I don't know what I'm talking about. So that will be right there. That's the intersection. I don't know why I was looking at some other number. It should be 97. Yeah, I actually had it here. I don't know what I was talking about. Okay, sorry about that. So that y2, can I just look at it again? Oh yeah, okay, 979. So it's a little further up here. So that's just a matter of the precision of our root scalar, but essentially it'll be using that intersection, close enough. That's around the hundredths place, which is pretty good accuracy. And then for mole fractions at least, and then we do another equilibrium line here, and then it just iterates. So we'll have pairs of these lines going down forward. So if you notice, that's just our next y up here. So instead of just doing something like y equals y2 now, I could just make this y. So hopefully that makes sense. And if I make that y, I think we can just start iterating this now. So I guess this is the intersection. And yeah, remember we're taking this loop out. So I'll do that after, but we need to loop this first. So maybe like for, I don't know, for I in range 5. And then we will need to move everything over. There we go. See if this works. Wow, nice. Okay, perfect. See, I don't know why it was saying numbers that are further. It actually goes exactly at the intersection. So it's actually working perfectly fine. I don't know. Maybe I can't interpret a graph well, but there you go. So you'll notice it will keep going, but if I do too many, eventually it will bottleneck since we reach a composition. Yeah, right there, where you kind of see how it's getting smaller and smaller. We're not progressing well since, I mean, I can jack this up even more. Oh, that's too much. That is way too much. Go back. Maybe 200 is, oh, 200 works. Yeah, we bottleneck definitely. Is this around our, it should be around our feed. Yep. So you notice that, I remember our feed is like 0.45. Yeah. So our feed is a molar fraction of 0.45. Notice that we're not getting any separation lower than that. Yeah. So bottlenecks there. So I'll actually move this out now that we're doing loops. So now this will also be, oh, that back and then rectifying. So you'll notice that we do need to start moving on to our stripping section once we pass our liquid mole fraction of our feed. So doing that, we need to, you can see that. In doing so, we need to set conditions in our loop so that we're not going way too far. In any case, it would be after our tie line, since we want to do tie lines for everything. It's just the equation we're using is different for our MEB line and our intersection. So we'll do something like if our liquid mole fraction is higher than our feed, then we want to use our rectifying, as we should. And then else, since there's only one other condition, we do our stripping. So I could say stripping. So stripping is different. We have to use our bottoms. We have a delta S now. I'm just reading through all these, honestly. So that's our MEB line. And then our intersection, we definitely need a different equation. Those are our equations from our balance at the boiler. So we would have a stripping equation, I guess. And then we would need to do the boiler, so QB. So those are all the things we need to do. Honestly, it's just the counterpart of these three things. We just do those again for our boiler. So let's do that. I mean, we can define them first and do it as we have finished it. There's two things, or I guess just one thing I'm thinking about, since right now, if I just copy paste this, and then if we have these parameters and put them as we need, it actually wouldn't be correct since we're graphing to the liquid enthalpy line. And this works because the intersection is with the difference point of the condenser at the top, but this time we would need to use the boiler difference point, which comes from the bottom. And if we connect the liquid enthalpy from the bottom, well, you're not going to have an intersection point. So the root would actually need to be first, and then we graph to the root. So I'll do it the quote unquote wrong way first to show what I'm talking about. I'll bring this up later. And then I'll fix it. So that's all I'm talking about. Yeah, let's just do these, honestly. So instead of QC, it's QB for the boiler. We have delta S for our stripping, and then our stripping equation. So let's do this one at a time. So QB will obviously be another balance we'll do, as we did here. But since we have QC, it makes things a lot easier. Delta R is, well, delta S is the difference point for our stripping. That's something we already know once we have our QB, our boiling power, or the power associated with the boiler. And then we just plug in our equation. So, yeah, I think we just go back to the iPad. I've been saying just a lot. I know we're not supposed to say that word. I have to explain it. So we understand. All right. What are we at? 1 hour 3? Okay. Hopefully this doesn't go along for more than 30 more minutes. Time flies. Okay. So another balance. Yeah, we could just think of this as in and out, honestly. I keep saying just. Okay. So in equals out. Let's do this. What is going in? We have our feed and our boiler power. And I guess you could say technically we're minusing a condensing, but I'll just add it to the other side, so condensing. And then also out is our bottoms and our distillate. Okay, still recording. Bottoms and distillate. So now we have to write these out. So what is the feed? Remember, there are flow rates associated with these balances, just like how we did. I keep saying just. Oh my goodness. Is our energy? Well, I split them up, but our energy balance. Excuse me. Our energy balances. Yeah, they're written twice. I wrote them side by side. So again, they're written with our flow rates right there after that substitution. Honestly, right here. So yeah, we need to associate flow rates with our energy balances. So feed, what's the feed flow rate? Obviously, we just have that as F. And then we have a enthalpy associated. For our enthalpy, we use our interpolation. Feed was all liquid, thankfully, so we use the enthalpy of the liquid, and we interpolate based on the composition of the feed. I think we use ZF, I think, for the more volatile component. Boiler, we have a flow rate associated with that, RB. Again, we not really derived, but we got that expression from limiting our initial conditions, or I guess starting conditions for our distillation column with the recovery rate. And then we define B using the mass balances. And then obviously we need a enthalpy associated with that. So that's another enthalpy of liquid. The bottoms, I'm sorry, this is the power we're putting in. I don't know what I'm talking about. So this is our QB, or that we're solving for. I'm sorry, I was thinking of bottoms and boiler. I don't know why. Condenser we already solved for. That's QC from the last, I guess, for the rectifying equation. Bottoms, this is what I was talking about. So bottoms has a flow rate of B, and then we, obviously both of these are both liquid. Obviously, I keep saying obviously too. I need to remove that. Okay. So both of these are liquid. We interpolate the liquid enthalpy at the bottoms composition, and then same thing. We have a distillate flow rate associated with that, and then another liquid enthalpy we interpolate, now this time at the distillate composition. So that's our equation. We isolate QB, so I would be subtracting this over, honestly. This is the nice thing. I can just do this, maybe. Like that. Delete, over. There you go. Awesome. Don't you wish you could do that in real life? Okay. Yeah, let's just write that out in our collab. Easy peasy. Up. And we go down. It'd be too big, so I'll do it a little bit at a time. So QB equal to QC. We have that condensing power plus the flow rate. We use enthalpy to interpolate. I need to multiply, or it gives me an error. Go. You don't really need a parentheses there, but I put one. The bottoms, interpolate liquid from the bottoms. You add that to our distillate. Again, interpolate liquid enthalpy from the distillate this time. And then we subtract our feed, like so, minus our feed, again, a flow rate, times our enthalpy, and liquid, our feed was all liquid, so we use enthalpy of liquid. There we go. At ZF is our composition. Remember, we can do ZF since our feed is 1. Our composition Z is just 0.45. So it'd be the exact same if we multiply them together. Okay, that should work. Let's take a look at that. Awesome. Yeah, pretty comparable. If you notice, the boiler, amount of power you need to supply your boiling condenser. Obviously, you're condensing and boiling, vaporizing the same amount of moles. So, well, it's a balance, so it should be relatively the same. Heat of vaporization is obviously is more because you need more to vaporize a liquid versus condensing, as we have discussed. And then we'll do our delta S. And delta S comes from, I think I put it here. There, awesome. Remember, we negated everything since the differences would have negatives on top, our original expressions here. So we use this expression, or these sets of equations for our our stripping section. So delta S, we have so HB again is the bottoms enthalpy associated with that bottoms composition we're taking out. So that's another liquid enthalpy. We interpolate at the bottoms, and we subtract our very big number, QB, boiler power associated with our bottoms. So that's joules per mole, and let's take a look at that delta S. That should be very negative. Yeah, wow, 434, and we're only at negative 77,000. Wow. Okay. And then now we need to define our stripping equation. But first, let's just, well, actually, I don't even think we'll be able to graph our lines until we go through all our loops. Well, yeah, we'd only be able to graph one line since you won't be able to find the next y. So, I mean, let's just do it. We already know what we're doing, right? So, yeah, let's define our stripping equation. Honestly, it's pretty similar. So this will be stripping, and we supply the same thing since, again, we're iterating from our last liquid mole fraction, and we connect that down to our vapor mole fraction. But you'll see that you actually need to take the root. You'd actually need to graph the difference point to the y in order to get the vapor mole fraction. So you're actually using your liquid mole fraction and graphing it all the way up to our using our liquid mole fraction and graphing our line from the difference point of the stripping to our vapor mole fraction. So that's what I was talking about with the root coming first. I'll do it like this for now, and then you'll see what I'm talking about. So let's just put in our just in this. Okay, so it's this equation. We're writing that out. Okay. I can't stop. It's like part of my vocabulary. Okay. Liquid at the current position. So enthalpy we interpolate from the current liquid mole fraction. That is so much. And then we just subtract. We subtract our delta S. Divided by, again, would be. Well, now this is heat of vaporization interpolated from our stage below. The next stage, and then remember, N refers to the current stage, and then vapor refers to the stage below. That's why we have Y2 and X. So interpolate liquid enthalpy from the current stage X. That is, you can't see anything when I'm typing. That sucks. Okay, subtracted, and then we do our mass balance. Subtract that over. We just negate it front. Our current X minus our bottoms. Remember, bottoms is the smallest. Since we're doing this in terms of more volatile component, you'd have less composition of our more volatile component in the liquid phase, especially at the bottom through all that separation. Divide by our Y2, the stage below, and what else? Yeah, X. I think it's just X. Now let's try that. Let me just go back now. Let me move this down so we can still see it. So if there's a problem, it's likely here somewhere. Okay, and now we copy paste. Remember, we're going to move these. Well, we need to move the root in front so that we can graph it. But in this case, it's okay for now, so you can see what I'm talking about. So we do from the bottoms. Technically, I mean, it still works since it's just a pair of points. But I like having to move the lower point to the bottom, but this should work as well. That's still the same, and then we use delta S, the difference point, same line, same graph, and then now we do root of our stripping equation. Did I define that? I did. Okay. Yeah, I think this should go pretty okay. If we have too many stages, you'll notice that we'll be iterating along the same line. So we can actually add a break line after this, but let's see if this works. Wow. That was fast. Okay. Oh, here we go. So this is what I'm talking about. Our lines are only reaching the liquid enthalpy. So we want the vapor enthalpies to show that we're not just grabbing them. And I mean, obviously the root knows what it's talking about. It's iterating and knowing where to get those, but we actually need to graph our MAB line to the vapor enthalpy. So let's do that. This is what I was talking about earlier. So now I move that. Now we want to get our vapor enthalpy. So that's our vapor mole fraction. And then we move this down, go up, and that corresponds to a vapor enthalpy interpolated at arc Y. So let's try that. There we go. We got them. So that's those are our lines. Those are the vapors. What is happening? The vapor. Let me get rid of this. Fine. Okay. Never mind. Sure. Whatever. Yeah, those are the vapor mole fractions we are using. And I'm not sure if we actually finished the number of stages, but let's add in our break statement. So that'll be after our tie line. Obviously, we want to do the tie line first before breaking. So I'll add another if statement, like if, so now if our, wow, my voice. If our liquid mole fraction is lower than our bottoms, then we break our loop. And now let's make this like 100. Obviously, that's way too much since we're almost finished, but there we go. We actually finished out. And it's about right here. Oops. Yep. There we go. Is it? Curious. Is there an extra line here? I think there needs to be another line here if there's another equilibrium, unless I'm crazy. Is there a reason why we're not doing that? Or is there extra equilibrium? Let's see. I mean, these are obviously different. 0.01. Yeah, 0.01 is our, since we have 99% in our distillate, 0.01 is our, so why are we missing a MEB line? Oh, I know why. Because I didn't move it up. I forgot. I said I was going to do it, and I didn't do it. Did I move it up? Yeah, no. This is the root. Okay. So again, you need to do the root first. There we go. There we go. Fixed itself. Or I fixed it. Root first because it ends on the tie line. Or on the MEB line. So if you want the next one, you need to do the intersection first. And then you graph it. Okay. Are we done? Yeah. Now we just graph our xy's, so that's really easy. You're just grabbing the pair of points. Remember, let's go back. I don't remember where I drew this out actually. Do I remember? Cannot say. Was it? Let's see. Is it A maybe? Nope, that was NRTO. So I don't. It was with our McCabe Theo, but essentially it's the XY diagram. So we need to grab pairs of points. It's our staircase at equilibrium. So we're grabbing every time we change points for our tie lines. So we'd be grabbing these points, the equilibrium points. Like so. We'd be grabbing all those points. So we need to grab every time we change our X and every time we change our Y. And remember that we have doubling points in our staircase. You remember we go from the operating line, well, 45-degree line to the equilibrium line, and these are at the same Y. And then when we go down to our mass balance line, our operating line, these are at the same X. So those X and Y's continue repeating, which is why we have to capture those points, I guess, in the at the same time. We can't just grab one X and then change a Y, since we need pairs of points to match up. So that being said, let's go ahead and define our equilibriums, equilibrium lists. You can see that here. That's too much. Okay. So set our lists equal to something. And actually, I won't put in the initialization. You'll see what I mean. We'll be actually missing a point at the start since we're interpolating here already. And we are interpolating from our distillate. We're actually missing our point on the 45-degree line. So I'll refrain on showing that for now, so you know what I'm talking about. And then now we want to append. So this is the first time our X and Y's change, where again, we're interpolating our Y from our distillate. So that's a new X. Remember, our first X is at the distillate as well, but I didn't put it in the list since I want you to see what it looks like in the graph. So we do the append of our lists at that x, and then we also append our lists at the y, the new y and x. Well, I guess it's just a new x. Well, we need to put a y. Okay. And then we do the same thing. We can just put this at the very bottom. If we put in all the loops, it'd be kind of contradictory when we can just, well, not contradictory, but just more work. Because it would do the same thing. But if we put it at the end of our loop, remember our loop goes through all the statements and checks them. This doesn't have a condition, so it'll check this at the very end. So whether or not, whichever condition it uses, stripping or rectifying equations, I should say, whether whichever equation it uses, it will always append the new x and y. And remember, we have a new y that we're getting from doing the intersection of our difference point and the liquid mole fraction. So, and remember, we need to do it in pairs. So there's a repeating, there's a new y. We're going horizontal to our equilibrium. So we need to, oh, I'm sorry. Yeah, new y is, sorry, it's a new y would be a vertical line. So that's a new, the same liquid mole fraction, but a different vapor mole fraction in terms of coordinates. So we have those, and now actually we already have the binary xy. So let's graph that and see if it's still working. Awesome, it's there. So now we just graph, let me copy paste one of these, our equilibrium. We can put this at the very bottom. Because why not? So this is our staircase. And we just graph our list of x equilibrium, y equilibrium. Got it? Awesome, staircase. And then if we want to draw our operating line, remember that is connecting the points of essentially just the bottom points here. Connecting all those, notice it'll be a slight curve of the number of stages we have. And then remember what I said earlier when I said I didn't initialize. We actually don't have our 45-degree line where the vapor composition and the liquid mole fraction, did I say that right? Vapor mole fraction and liquid mole fraction equal each other. So there's actually no line on the 45-degree line because I didn't initialize that. So I'll go ahead and initialize that. And then now it should appear. Let's go ahead and zoom back in. There you go. Right there, 0.99. Remember, that's our desired, or what we set as our condition for the distillation column. And then now the last thing is connecting the operating lines. So I copy paste, yes. And then this will be, operating line. And honestly, that's just index slicing of our list. So that's all the points. Did I do that? Okay. All the points to the very end, and then so this is from start to end, and then this second colon denotes how many steps we're taking. So normally we leave that blank, but if we have another colon, we do every other step. So that's 2, and this would be the exact same thing, except for the equilibrium. So 2 colons and a 2, like those lines. Awesome. So yeah, these are our Ponchon-Savarit and McCabe-Thiele diagrams, and I believe the last part of the question is asking, let's just check. Can I go split? Is asking, where are we? Yes, the minimum and infinite stages. So I believe later on, well, in class, this is mentioned at the end of class where we talk about the Fenske-Underwood equations. So let's talk about the infinite reflux first. So infinite reflux, if you remember our, infinite reflux refers to, well, our McCabe-Thiele has a slope, the operating line of our McCabe-Thiele has a slope of r over r plus 1. So for a minimum number of stages, is this being associated with an infinite reflux? Well, all that means is that with infinite reflux, you're increasing your r so much so that the numerator and denominator become indistinguishable. So essentially that slope is 1. So eventually we'll have something close to our 45-degree. Honestly, let's just do it. So where are we? So if we increase our reflux so much, like 100, that's huge. So again, what that means is for, so yeah, I'll explain this. Let's full screen here. So infinite reflux, again, our R is so high that in the R over R plus 1 slope of our operating line for our McCabe-Thiele, seen here, our operating line, which was this blue line, has overlapped our 45-degree line, and that's because the numerator and denominator have become indistinguishable, so it mimics a slope of 1. So that was our 45-degree line. That normally has a slope of 1, and then now the operating line has become that. So once it reaches that scenario, you'll notice that it will reach that slope of 1, and then now we can only draw this staircase. No matter how much we increase the R, you will have that operating line on that 45-degree line, and you'll have a set number of stages that you can go. So that's what that means. And then for a set number of stages, well, I guess for a higher reflux, I should say, higher reflux refers to, well, let's think about it in terms of numbers and values. So if we have a reflux of 100, like I said, so remember reflux is the ratio of our reflux we're putting back. So that's our liquid that we're returning from our condenser over our distillate. So if it's 100, that means for every mole of our distillate, we're returning 100 moles of liquid coming down. So again, our vapor would probably be 101 moles coming up, and then into our total condenser, our condenser condenses all of that, and we take out 1 mole of distillate. So you can imagine in our Ponchon-Savarit, our the enthalpies, or I guess the power associated with our condenser right here, the difference point, and then for our condenser, and then our stripping, well, it's our boiler. Those the power associated with those would be so much. So that's why it's so much relative to our, remember, all these lines didn't change at all. These are actually the same lines, if you remember, around the 200, 300,000 mark. Those are the heat of vaporizations and heat of the liquid associated with our equilibrium vapor and liquid mole fractions, respectively. And of course, our enthalpies are so high since we're condensing and vaporizing so much moles, essentially. So that's why those two graphs are like that. And yeah, I think I already explained that. So, and then going back to the I think I went backwards, but that's okay. So we talked about infinite reflux. Now the minimum reflux ratio, so that's the Underwood equation that we were talking about at the end of class. I think this lets you calculate, the minimum reflux ratio. So if we decrease our R too much, remember our slope of R is R over R plus 1. Sorry, I'm trying to minimize these windows. R over R plus 1. If we decrease our R so much, approaching 0, well, the slope of the line approaches 0. It becomes a horizontal line. But you'll notice that if this operating line becomes horizontal, like so, you're not going to get any separation, at least beyond the feed, if it is 0. So actually, let's just show you. If I pick a really bad number, like 0.01, maybe 1, we won't make that much headway. Yep. Yeah, we don't even... Yeah, essentially our operating line crosses the equilibrium, and you don't get any more separation. So, you even see that? Yeah, it's basically a straight line. So, let's choose something more reasonable so you can see how it kind of bottlenecks. And that's the whole idea of a minimum reflux ratio. You need a minimum amount so that you can cross the feed line, so that your operating line isn't crossing the feed, and you can actually pass from your rectifying section to your stripping section. So I don't know, like 2.2. Is that too much? Yeah, so I think we need more stages since we're no, I think we're actually bottlenecking still. So yeah, if you zoom in, we do take, how many steps do we take? 100. So yeah, this is actually 100 steps. And you can kind of see we're in the hundredths of a mole fraction, and it actually kind of breaks here where you're outside your equilibrium curve, which is not possible. So I don't know, something more reasonable where we can still go around it, but it's not quite enough. Maybe 0.5. Yeah, 2.5 actually works, but you do see where we are starting to bottleneck around this area. So that's this whole idea. Our enthalpies didn't change, but you just notice we have a lot more stages. So obviously going from infinite reflux to minimum reflux, you're going to increase your number of stages, because with infinite reflux, well, that's your minimum number of stages. So if you have, you're approaching your minimum reflux ratio. Is that what we're doing? Sorry, I think I'm confusing myself. If we're approaching our minimum reflux ratio, you need to take more steps in order to get past this squeeze point where we go past our liquid mole fraction, because the slope, well, it's r over r plus 1, so if it's approaching 0, we have that bottleneck at our liquid mole fraction, and we have to draw many, many staircases, a lot more, in order to go past, since there's very little separation until you go past into our stripping region. So these are important because, well, with the is it Fenske equation? Fenske, for the infinite reflux, the minimum number of stages. Well, that helps with, well, binary, you can do the graphical analysis just fine, like how we're doing, but with multi-component, it gets a lot more difficult. So with that computational method, without doing the graphical analysis for a multi-component, then the Fenske equation becomes very helpful, which I'm pretty sure we're going to be doing multi-component very soon. So that's the importance of the Fenske equation. And then with the Underwood equation right here with the minimum reflux ratio, usually we find that, we compute that as well, and you know where to start in terms of your distillation column. So you calculate your minimum reflux ratio, make sure you're above it, maybe multiplying by some scale factor like 2. So we have some baseline to design your distillation column. And then obviously with that point, from that point, you kind of decide, well, how tall, what kind of, well, how tall is my column? What is the reflux ratio I want to choose? Since again, with infinite reflux, remember how our enthalpies were scaling to like the millions of joules. So again, infinite reflux, as you approach a higher reflux, you would need more power. So obviously that's more expensive, more power for our condenser and our boiler to handle those number of moles going through, as well as the flow rates going through, since you need a wider column in that case. So again, optimizing between a wide column, a more expensive column, and a tall and skinny column with more stages, which kind of associates with this minimum reflux. So obviously, again, minimum reflux, I think I wrote this down actually. A minimum number of stages for infinite reflux, and an infinite, well, quote unquote infinite, you could take many, many steps, but not actually approach, not actually go beyond our feed composition for the minimum reflux. Remember that you can take very many steps, and remember those steps were, oh, can't see that. I was zooming in on the bottleneck here. So obviously you take more steps as you have less separation until you cross that, in which case you get better separation in the later stages. So hopefully that makes sense. Still getting this divide by 0. I have no idea since it's working. So that's all of it. I'm going to return this back to what we had. We have 3.25, 3.5. Okay. So I'll leave it at this. There's a lot of talking. Wow, this is a long video, 1 hour 90. So not 1 hour 90, 1 hour 30 or 90 minutes. So yeah, I guess this is the end. If there's anything else from me, you'll hear from me after I pause this. But other than that, thanks for watching.